Okay, it starts now. Good. Okay, so if there are no questions, then I will finish up this chapter, introduction chapter. And now we are going to talk about operating system concepts. Okay. We did our hardware review. We did our main operating system types review. Now we are going to talk about operating system concepts. Basically, we will talk about, this is just very small introduction, very, okay. This is about CPU, this is about memory, and this is about I/O and file system, these two. Okay, so let's get going then. Okay, so the process is basically a program in execution. That's the definition. Okay, so we know what a program is. Program is just a formal representation of an algorithm in a known programming language. A program is supposed to run. When you run the program, okay, on a computer's memory, it becomes a process, okay? So what is the difference between a process and a program? Program is a static piece of code which can be run, but process is the running program, okay? So what does that mean? If a program is running, okay, if a program is running, then I'm going to show it this way. This is my memory, okay? At the bottom of my memory, my code, this is what we call text, instructions, and this is address 0000. And on top, I have my maybe the data or the heap, maybe, okay? And data is growing upwards. And at the top, I have my stack. And stack is growing downwards. If a program runs, okay, that means what? CPU is using it, CPU, and CPU has registers in it, right? Register number 1, register number 2, stack pointer, which points to a position on the stack. Okay, maybe I should get a new pen. Yeah, get a new pen, and this pen needs to be okay. Here is my pen. Let me change the color of it. Green is good. Okay, and this. Okay, good. So this one is stack pointer is pointing to somewhere in the memory, is just top of the stack, right? That's the stack pointer. And what else? I have my program counter and status world. Okay. These are special registers, and for each running program, I have to have this. Otherwise, CPU cannot execute, right? That's the meaning of the CPU. So back to the definition of the process. When I talk about the process, I talk about a running program. When I talk about running program, I talk about the inner states of the CPU. So a process is basically a program in execution. And in this program, basically a program in execution, I have my address space, which is this one. This one is my address space. Okay. Most of the time, this is a logical address space. What does that mean? It means that each program, each process has its own address space. It is logical. This is not physical, but the program thinks that, the process thinks that it has this physical address space, but it's a logical address space. It shares the physical locations with some other processes in a smart way, of course. This is the address space, and then for each process, I have this data. I have registers, open files, and other data. And I keep them in a table. So in my operating system memory locations, I have a table like this. Okay, this is called process table. And in this process table, process number 1, process number 2, process number 3, dot, 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 up to process number 305. How many doesn't matter. So inside this process table, I have this information. I have registers, the open file information, and some other data. Okay. So where is this process table? Where do I keep this process table? Question.
Memory.
My volume was way down. Okay. Say it again. Somebody said something.
Memory. Memory.
Of course. Yeah, that's true. Of course, we keep it in the memory. An operating system since it's a process too, it has this kind of a memory structure, it's address space, right? So operating system has its own data space like here too, okay? But the thing is this, it says that inside the process table, I understand that you keep your open files. Open files, I understand it because each process has their own open files and etc. But how about this registers? It says that I have some space for the registers, right? R1, R2, dot, 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 R64, whatever. Do I keep my registers in my memory? Before that, I said that registers are in the CPU, right? But this guy says that the slide, the registers are kept in the memory inside the process table. Am I making a mistake here?
Maybe when a context switch happens, it stores the register values to the memory.
Exactly, Matt. Say it again, but slowly, everybody can understand.
When a context switch or some interrupt happens, process table records the register's value at that time.
Exactly. How many registers do I have? How many register R1s do I have in my CPU? Just one, right? But I have 300 processes here. So each process has their own R1s, right? When the process is running, of course, the process is using this register. When the process is blocked, it is not running, it is not using the CPU, then I keep this register data in there, okay? So this is kind of a saving place for all of your data. Okay. And context switch means that saving all of your data to this location and loading, okay? Context switch means that saving all of these data to this location and loading up all that data to the CPU. That's what the context switch is, okay? Of course, this process table is not this simple. And next chapter, we are going to see what kind of other things we are going to have in the process table, okay? Other than the registers, I have lots of timekeeping data. And if you like to know what kind of things you are keeping in your process table, whatever operating system you are using, I am using Windows right now, okay? I go there and I open the processes. These are my processes. Okay, and I have lots of things working in here. I don't know how many pages and pages of processes. Most of them are operating system processes. Some of them are application processes. For example, this one is a Teams is a application process. This one is an operating system process. Okay, and this one is an application, operating system application actually, and etc. This one is an application, and I can add many more data. For example, how much percent of the CPU I am using, okay, and how much I had used is kept on my process table. This information is very useful when I do the scheduling. Okay, when I, as an operating system, when I make a decision to know which process is going to use the CPU, I look at their CPU usage statistics. If one of the processes is not using the CPU for a long time, then I switch to that one. I think these are, yeah, okay. These are better. These are my process IDs, right? And this is the state of the process. This is how much I am using the memory, and this is if it's a 64-bit application or something else. I think I can, let me see. Okay, let me sort it out, sort it for this. See the very small process IDs, they are all system processes, and the last ones are like very recent processes. Okay, very recent processes. And I like to, there should be one way of adding more. Okay. See this one, I can change the priority of the process. This is the priority of the process. If I make this very, very high, then during the scheduling process, this process will get the priority. Okay. How about this one? No, I didn't get the other useful statistics of, maybe I should add some more. This one? No, didn't work. Anyway, so this kind of data is available. This kind of data is available for all the operating systems, as long as the operating system is a sophisticated one. Okay, and you can list them out. Okay, so small introduction to processes. Yes.
I didn't fully understand the difference between registers in CPU and process table.
If I had only one process running on my computer, this is the picture, right? It's as simple as this. I have my data, physical address space, and I have my CPU. And I have a single process, and that's it. It's like the computers of the mainframes of the 1950s and personal computers of the 1980s, okay? There is a single process running, that's it. And then no operating system. That if that was the picture. But if I am running 300 processes at the same time, and I have a single CPU, that means what? Only one process can run, the others have to wait. When they wait, when they are blocked, where do I keep this CPU data? I keep them in this process table, okay? So this R1 is basically a copy of this R1 when the process is not running, okay? Of course, when the process runs, I use this R1. Otherwise, if I had to go to the main memory to get the R1 values all the time, that would be very, very slow. Remember, it is 100 times slower than accessing the CPU, right? In terms of...
It's just data in the table, right? Process table.
Yes, it's just the data. They are not registered. They are just copy of the registers. Okay.
Thank you, sir.
Okay, so that was a good question. Any other questions?
I have one. In Task Manager, what we understand the CPU usage.
Okay, go to Task Manager again. CPU usage means that, okay. Is that your question? What is CPU usage?
I mean, what I understand, for example, CPU usage is 100, for example. I can't clarify the numbers. What does it mean?
It means this. CPU, let's say, for 1 second of the CPU, okay, for full 1 second of the CPU, almost 10% of the CPU time is spent for Microsoft Teams, okay? So rest of that, like 2% it is for Window Manager, okay? And it says that for currently, I am using 15% of the CPU time for all these tasks. That means what? 85% of the time CPU is idle, it's not doing anything. If I go to the picture that I had drawn before, if this is my timeline, okay, and at this position, if this is process number 1, let's say it used the CPU for 10 milliseconds, then operating system used the CPU for 2 milliseconds, then process 2 used the CPU for, let's say, 15 milliseconds, etc. Then in this part of the timeline, nobody uses the CPU, it is idle. Why nobody is using the CPU? Because process 1 and process 2 is blocked. Maybe they are waiting for some disk data. Maybe they are waiting for some mouse input. Okay? What does a Word program do if you don't type anything, right? Sometimes it takes a backup, and most of the time it just waits, it is idle. So if this whole thing is, this is like 100 milliseconds, and as you see, 28, right? This is 28, and rest of them is 72. Okay, so it is like 72% of the time CPU is idle, 28% of the time CPU is busy. That's the CPU usage. Okay.
Okay, thank you.
What happens? The CPU usage becomes 100%.
Computer gets slow.
What do you mean computer gets? Computer is always the same speed. It doesn't change its speed. The clock rate is clock rate.
We feel it gets slowed because the context switching gets hard.
No. You are not answering my question. Computer is always running at the same speed, same clock speed. It doesn't get faster or slow. But you said that the computer gets slow. What do you mean by computer gets slow?
I mean, the interactivity is getting slow.
Exactly. Yeah. It appears that I am not getting responses right away. I have to wait a little bit more because I have to share my CPU with many other processes. But sometimes if the operating system is good, okay, it is optimized, even at the 100% CPU utilization, the computer may not appear to be slowing at all or unresponsive. Because I have enough CPU time, I can respond to it. But if I keep using too much memory, close to 100%, then the things get very, very grim. Why? Because I don't have enough space to do the context switching, right? When I switch from one process to another process, I have to keep, it's like this. Okay, this is my total memory, physical memory. Okay, and on this computer I have 16 gigabytes of memory. Okay, this is the operating system. This is process number 1. This is process number 2. This is process number 3. And this is process number 4. But I have to keep, let's say 5 processes in this memory so that I can switch between them. I don't have enough space. What am I going to do? I am going to, this is my disk. I show my disk this way. I need to, for example, take this P2 and write it to disk. P2 is on the disk now. And I need to load P5 from this to this location. Okay, but as we have seen, writing stuff to the disk and reading it back takes millions of times more. Okay, millions of times more time than switching. So it is more expensive than the context switching. So the main problem most of the time becomes, okay, not the CPU utilization, but it is the memory utilization. Okay, it is the memory utilization. If the memory utilization is too high, then you are going to do this switching back and forth between the disk and the main memory, and that's going to make your computer seem a lot slower. That's called trashing. So with the trashing, your computer spends most of its time going back and forth between the memory and the disk or the secondary storage. So CPU is idle actually. CPU is not doing much, okay? CPU maybe is used 10% of the time, but CPU uses its time to do this trashing, writing back and forth, okay? Instead of using useful work, it is doing this, and that will be a bad thing. So don't get surprised that your computer is sometimes unresponsive. When you look at the CPU utilization, it is 10%. Okay, so what is happening? I mean, I have enough CPU idle times, but the problem is your memory. Okay, your memory needs to be okay, large enough so my memory now, it has large enough empty place, so I don't have to trash. I don't have to go to the disk back and forth. I can switch between the processes very fast compared to disk trashing, okay, because I have enough space. But if I keep adding more data, if I keep opening more windows and etc., then I will be in trouble. Okay, let me close this edge thing. Did it go away? Yeah. So it has dropped some memory. So it was very interesting. When I try to close something, the memory increased a little bit, then it dropped. We are going to see why this is happening when we look at the memory chapter. Okay, good. Okay, so that was a good question again. Any other questions like this? As I said, the chapter number 1 is the maybe most important one because you understand the main concepts here, okay? The address spaces, logical memory, and the context switching and that kind of stuff. The rest of the book is kind of complementary information, details of how the things are done. Okay, let me continue then. So we talked about the processes. Usually the processes are related this way. When the computer starts, okay, when the computer starts, there is only one process, okay? There is only one process. We will see what this process is when we in the later chapters, okay? This process, okay, constructs new processes and tells the operating system that, okay, I have a new process now. And those processes become the child process of this process A. And B can say that, okay, I'm going to make 3 more processes. So this makes a process 3 hierarchy, okay? And usually they help each other, okay? A asks B and C to do something. B asks D and E and F to do something, okay? Whenever they are done, okay, they communicate back the data to the parent process, okay? So they have to communicate with the other processes. This is called inter-process communication. Inter-process communication. We will talk about this a lot, inter-process communication. It is very simple to communicate between 2 processes. All you do is you use a shared data in the memory. If this is my memory, if this is my process A, and if this is my, let me show you this way. This is process A, this part of the memory, okay, and this is process B, this part of the memory. As you see, I am sharing some space between these. If I write some data to the space, A and B can communicate between each other. Okay, this is as simple as this, inter-process communication. But although the communication is simple, there are many problems that can arise from this kind of data sharing. Okay, data sharing. Most of them are called race issues. We'll talk about those. Okay. Inter-process communication synchronization. I have to do it in a synchronized way. The main problem happens this way. While A is writing something to this area, if B is reading it at the same time, that becomes some chaos, and I have to solve this problem. And if both of them are writing to the same area, that's even more problematic. We have to solve these problems, and we'll talk about it when we talk about the process.
Sir, I have a question.
Sure.
D, E, and F are sharing some location with A or only B?
That depends on your operating system. That depends on how you created your processes, and both of them are possible, what you are saying. Or they might be completely using very different memory spaces. Okay. So it depends on how you created those processes. It depends on what kind of inter-process communication mechanism you use.
Thank you, sir.
Okay, by the way, in Windows, from the kernel of the system, we don't have parent-child relationship. Okay, there are no parents and childs in Windows in the kernel. Okay, they kind of make it look like they have parent-child mechanism for you, but in the kernel we don't have it. At least they have, at least how they document it this way. But in Unix and Linux, of course, we have parent-child mechanism, definitely known. And if you kill process A in Unix, all of the child processes, okay, that belong to process A will die too. Okay. Good. These are the processes. Okay, we are talking about again processes, address spaces. We talked about address space and process. Let's look at files and input and output. Okay. I need to keep my excess data. I can't keep everything on my memory because memory is too small. Okay, that's one thing. The second thing is memory is volatile, right? When the power goes off, the memory is off too. I lose all the data in my memory. So as a permanent storage, I need my secondary storage, and that's where the concept of file comes in. File is just a structure, data structure, that keeps related data on our secondary storage. Okay, and compared to your main memory, which we measure in terms of gigabytes nowadays, okay, our secondary storage nowadays we talk about terabytes. So it's like most of the time thousands of times larger, and it is most of the time thousands of times slower, larger and slower. Okay, so that's the idea of the secondary storage, and files are the way, okay, we organize this data. If you keep your related files together, that becomes a directory. Okay, so it's a way of grouping files together. And in our PC operating systems, such as Windows or the Linux, okay, we call them either directories or folders. And in order to find the files on a secondary storage unit, I need to know its address, and the address is known by the path name, and you know about these, or we will talk about them when we come to the file systems. Okay, in this book there is a complete chapter about file systems. Good. I'm going to skip this one, and let's look at this rule. Okay, at the end of this chapter, the book discusses this rule. Okay, this idiom maybe. It says that it is directly taken from biology. Okay, development of an embryo ontogeny repeats, okay, the evolution of the species. Okay, so what does that mean? For us computer scientists, we say that each new computer type or each new operating system type goes through the same development as ancestors. What does that mean? What does that mean? It means that, let me skip a little bit. It means this. In 1960s, the mainframes had only 128 kilobytes of memory. That was it. Since I don't have much space, okay, I can't keep more than one process in my memory, okay, so there was no operating system. And I can't keep a compiler on my memory, that's too expensive, so I write all of my programs in assembly. Okay. Later, when they have invented making smaller transistors and more efficient transistors, PCs became feasible. They are cheap enough now, but they had the same problem. They had only the very good PCs, they had only 64 kilobytes of memory. Okay, and assembly was used to write most of the time programs for those PCs. So in these 20 years, we had to go back and we have to write our programs in assembly. And nowadays, or maybe 10 years ago, smart cards were doing the same thing. We have these kind of memories available on our smart cards. And smart cards, as you know, as we have learned last time, they have their own CPUs and operating systems, but they are so small, they are so weak, their CPUs and memory limitations. We have to write our code in assembly to make it more efficient. Okay, so again, we are doing this, we are living the same thing again. Each new type or species of computer, it goes through the same development as the ancestors. That's why in this book, we look at the older systems, obsolete concepts. Those computers are not used at all, okay? They are done. They are only in the books, but the ideas they have introduced, they are fundamental ideas. And whenever a new, smaller type of computer and operating system is invented, we have to say that we have to solve the same problem over and over again. Okay, over and over again. The thing is the thing happened. The thing happened with the CPU times and the memory, also the protection too. Okay, in 1960s, 1950s, there was no protection. Remember what the protection is? I think I asked this protection. Protection is each process has its own address space and CPU. They think it that way, and they have no permission to use other processes' memory or the resources. So the hardware provides this protection mechanism. Even if I want it, even if I want to intentionally modify other processes' data, I can't do that because there is the protection provided by the hardware. Okay, that's called protection hardware. And in 1960, we didn't have any protection hardware at the beginning. In 1980s, okay, this popular CPU, it had no protection, okay? That's why we didn't have many operating systems that could run more than one process on this processor. And the same thing is happening today. Many embedded systems, which are specialized computers, they have no protection. So at a given time in history, there is always some kind of a computer that doesn't provide any protection mechanism, but there has to be some kind of an operating system there too. So we are facing the same issue over and over again. That's why we like to go back and we like to talk about the history a lot in this book and in this discussion of the operating systems. We are learning many things. We are learning about operating systems. We are learning about the computer history, and we are learning about where the main concepts of computer science come from, or the computer engineering come from. That's what we mean by ontogeny recapitulates phylogeny. Okay, good. I keep talking about Altair. Well, this is Altair is a star in the sky. It's an Arabic scientist. It's a very bright star, and they named their computer after the star 88. Okay, I kept talking to you about this one, and this one didn't have any operating systems. when you run it, you have to program everything. Let me see, I can, okay. Why can't I do, I crashed something. Okay. Using my other screen. Yes, I am in now. Okay, good. Multi-boot loader, yeah, okay, good. Do you guys hear what I am hearing? I don't think you can hear it, right? Do you hear it? Do you guys hear it?
No, we can't.
No.
You can't, because I need to, when I share it, I need to turn on the sound. Okay. So this is just a, see, this part, this is just a teletype, mechanical typewriter, okay? When you punch something on this keyboard, it makes a punch in the, it punches a hole on this tape, okay? So your program is stored on this tape, okay? So when this computer is started, maybe you can read your program from this tape, but you need to have some kind of a program that reads this data, right? So how are you going to read that data? This guy says that I am going to load the program to load this tape. And this is how it is.
Up and running on an Altair. All right, so first of all, let's go over to the Altair, and we're going to have to enter the bootstrap loader, because as you recall, when the
So he's going to enter the bootstrap loader, and the bootstrap loader is maybe 20 bytes of program that says that read something from the IO port, this number, and do this until you hit the end of the tape. So it is a simple loop, okay?
Altair boots up, it has nothing inside it except a bunch of empty, uninitialized RAM. In order to read from the paper tape reader, we're going to have to input a small bootstrap loader that gives it just enough smarts to accept data from the tape reader. That tape reader then will read in the tape that you would have purchased from Altair. First part of that tape reader is another more sophisticated loader called the checksum loader that then turns around and reads in the rest of BASIC off a tape.
So this guy is going to load a loader at the beginning, bootstrap loader, very simple one. So that simple one is going to read more sophisticated loader from the tape. And that program is going to load the rest of the tape.
All right, the bootstrap loader would have been provided in the manual you got from Altair. For our particular configuration, we're loading BASIC version 3.2, 4K BASIC, and we're using an SIO port. Those two things tell us what bootstrap loader to put in. So I'm going to go ahead and put that in now, starting at location 0.
So going to load something to address number 0.
All right, the first 2 bytes are 41 and 256.
41 and 256 is going to be loaded in the first 2 bytes.
41, we'll deposit
By
that in
playing with the
location 0.
switches.
And then 256 goes in the next one.
So this button, it says store, okay? just gives an address, gives the data, and presses this button to store.
Location. Next two bytes are 17 and 61.
17 and 61, store and store, right?
22 and 0.
22 and 0. These numbers are, okay, this is how you program your computer using the machine code. Okay, this is not assembly, this is machine code. Okay, you are just entering numbers. That's it. And these numbers, they are provided by the manufacturer of this computer. Say that, okay, enter this program first to load your program from the punch tape.
333 and 0. 17 and 330.
Okay. So how do you know that you made a mistake? You don't.
333 and 1.
You have to do it from the start.
275, 310.
Okay, so this is a very, very basic
5 and 167.
operating system, you might say, but it's just to load a program. That's it. So I wouldn't call it an
300,
operating system,
351.
just a bootloader.
And 3 and 0.
3 and 0. Okay.
All right. Now at this point, the program has been entered. That's the bootstrap loader with enough smarts to read the paper tape. But before we input the start the paper tape reading, we have to tell the loader and BASIC what type of serial port we're using. And in 4K BASIC, the first 6 positions or so were used to tell that. In later versions of BASIC in the loader, these 4 told BASIC what type of serial port was used. These 4 told the
So
loader.
it's you are telling the loader what port number you need to use to load the data.
We're using an SIO board. In that case, these bits all have to be 0 for version version 3.2 of 4K BASIC. All right, so now it's ready to run. However, the instructions say to start the teletype paper tape reading first before you hit run on the program. Now we're going to want to run from location 0, so I'm going to do a reset to get us back to location 0. All right, now let's zoom out a bit. And
Program counter is showing the location number 0 now, but it's not running anything.
take a look at the teletype.
So I think he's going to start the
If you take a close look at the
teletype.
paper tape, you'll see that we're in a very repeating pattern over and over. That is the leader. Turn on the teletype. And
Very
I'm
noisy
going to hit
teletype.
run. Start the program on the teletype, on the Altair. Now, if you look over here on the Altair, what you're seeing is the bootstrap loader running. That's the light pattern you see. And when it's done loading the bootstrap loader, we'll see the light pattern change when it jumps into the checksum loader that then turns around and reads the rest of BASIC. Now, that's about 256 bytes worth by the time it goes through some leader and the loader. Okay, they're just switched. So this
So it switched from the bootloader to the more sophisticated bootloader that had read from the teletype.
point, the second stage loader is running, and it's now going to continue to read the rest of the tape, which has BASIC on it.
It is reading the basic interpreter, not an operating system. It is reading the basic interpreter. Still, this computer doesn't have a operating system. It just has basic interpreter.
We look at this tape, you can kind of see here's the end of the checksum loader, and here's now the start of reading in BASIC. All right, well, this will continue for a very long time. It'll end up eventually putting quite a pile of paper on the floor.
All it is reading is 4 kilobytes of data. He says that it's a very long amount of time. Yeah, it is. It's going to take some time, but it's going to be like 4 kilobytes of data. That's how the mechanical stuff is slow.
It takes about 7 to 8 minutes to load all of BASIC at 110 characters per second. 110 baud, 10 characters per second. We're going to do a video cut and come back to this right before it finishes loading.
And by the second?
All right, the moment of truth is getting close. Just about out of tape here. You can see the end of the tape coming up. downloading. We hope to see basic sign-on. All right, that's it.
So it is asking a question, what is the
Nice
memory
when that
size?
noise finally stops.
See, it says memory
Okay,
size.
hopefully you can read that. It's asking memory size. We'll just hit return. Terminal width, we'll just hit return. Want sign, let's say yes. All right, we're up and running.
Okay, total of 61,400 bytes free, because 4 kilobytes is used for the basic. We have a computer like that now. So you
Right,
write
print
a simple
2 plus
program, print 2 plus 2.
2, see the answer there is 4.
4. So as you see, there is no terminal. This guy is using this teletypewriter as an input device and output device. Okay, so this was in 1975. That was how you do your computing with maybe $5,000. So this computer plus the teletypewriter, everything, it is $5,000. There is no operating system in 1975, but in 1955 they were doing the same thing with the mainframes, and we will keep doing the same thing over and over again using this kind of primitive input-output methods and primitive bootloaders and etc. Okay, I think I am way out of my time. Maybe I should take some break if there are no questions. So watch the rest of this video or the complete series, okay? And later they added more stuff to this computer, Altair 8800, and well, they are more sophisticated input-output stuff, but they are not really as sophisticated as what we are using nowadays. But watch the whole series, and I'm going to put this. I am going to put the link in here. Maybe. Okay. Good. Okay, let's take some break. During the break, I will stop recording. Let's be here around 9:45. Okay, break.